Hello, everyone. My name is Xingchen Li. I'm a PhD candidate student from Zhejiang University. Thank you for watching this video. I'm glad to share our work, titled Rethinking the Evaluation of Unbiased Scene Graph Generation. Scene graph generation is a task to convert an image scene into a visually grounded graph structured representation. The nodes represent objects in the image and the edges represent pairwise visual relationships between two objects. This graph-structured representation is able to support many downstream vision and language tasks, like image retrieval, image caption, VQA, and so on. However, it is hard to properly evaluate SGG models due to the intrinsic complexity of the task and several inevitable annotation characteristics of SGG datasets. Firstly, the annotations of SGG datasets are highly incomplete. It is unrealistic to exhaustively annotate all reasonable visual relationship triplets in one image, thus lots of positive triplets are missing. For example, the relations between cat and lamp may be missing in the annotated ground truths for the example image. Secondly, the data distribution of predicate categories is long-tailed. Head predicates always have much more samples than tail ones, leading to severe bias for model evaluation. The predicates for the head categories dominate recall performance. To observe the performance on each predicate category and treat each category independently, recent work exploits mean recall for evaluating unbiased SGG. However, we find that there are still two overlooked issues by mean recall that makes current unbiased evaluation vulnerable and unfair. The first issue is that the default mean recall unintentionally breaks the category independence when ranking across categories. It aims to output top K predictions for each image by ranking their confidence scores. However, the predicates in SGG datasets are highly correlated and there might be multiple reasonable predicates to describe the relationship for one object pair. For example, in this image, the predicate near and behind are both correct for the pair lamp and laptop. However, SGG is annotated following a single label paradigm and only near is regarded as the ground truth. In such a case, the predictions of those predicates sharing high correlation with others will receive lower confidence scores after the normalization for single label classification. To observe the influence of predicate correlation on evaluation by a real dataset, we visualize the output distribution for each predicate category based on one classical scene graph model, motifs. The left figure is the log-its distribution of motifs model. The right figure is the log-its distribution of motifs with de Biaside strategy, reweight. We can see that reweighting strategy can alleviate the bias on the head predicates to a certain extent. However, we can find there are some ubiquitous correlations among some predicate categories. For example, the samples annotated as wearing normally output high scores on its alternative predicates as well, like wears, has and in. Similarly, it also occurs between walking on and standing on, of and belonging to, and so on. As a result, the normalized probabilities of the predicates with high correlations after softmax are suppressed relatively compared to other predicates, like wearing and belonging to. In the subsequent ranking process, they are then less likely to appear in the top K when ranking across categories, leading to underestimated recall scores for those categories. Since each predicate category in the dataset has different correlations with other categories, it is unfair to rank their predictions together. The second issue is that the standard mean recall assigns equal weights to all predicate categories and neglects the compositional diversity of predicates in subject-object categories. However, we think this category-wise averaging strategy cannot reflect the rich structure of predicates on composed relationship triplets. To observe the compositional diversity of different predicates, we count the numbers of all possible composed subject-object category pairs for each predicate category in VG dataset. As shown in the left figure, we can see that the compositional diversity of different predicates varies greatly. The head categories typically have more generic semantics and can be applied to plenty of subject-object pairs, while the tail ones are more specific and usually possess limited compositional diversity. However, mean recall unconsciously assigns high weights to the samples of those predicates with limited compositional diversity. Here, we devised a simple experiment based on motifs model. For the last n tail predicate categories in left figure, we find out all their possible composable subject-object pairs in the training dataset. Then for each composable subject-object pair of predicate category C, we replace their predictions as the predicate C at test. From the table, we can find that the results on mean recall are continuously improved with the increase of n. We can observe that the predicates with limited compositional diversity have a stronger correlation with subject-object priors, which can be simply improved even without visual information. To handle the above-mentioned issues, we provide two complementary metrics to improve the current unbiased SGG evaluation benchmarking. To treat each predicate indecently, for each image, we independently rank and output top K predictions for each predicate category to calculate their own recall scores on this image. Then we obtain the recall on each predicate category by averaging the corresponding scores over all images. The final score is the averaged value over categories. We call this metric independent mean recall. By considering the compositional diversity of different predicates, we suggest reassigning weights to each predicate category according to the complexity of their compositional space. We count the number of composed subject-object pairs for each predicate category, and reassign weights to each predicate category. In addition, we devise a simple baseline and improve unbiased SGG performance greatly. Previous work counts the co-occurrence of subjects, objects and predicates in relation triplets and obtain a statistics matrix from training dataset. They usually aggregate the dimensions of subjects and objects to find the frequent predicate under the given pair. For example, on is the most frequent predicate under the pair car and street. However, this statistical prior actually collects the frequency bias and cannot reflect the intrinsic correlation between predicates and objects. We find that it is more reasonable to observe the distribution of objects over each predicate to find the correlation between predicates and objects. For example, if we count the most frequent objects given parked on, we can find its most relevant object category is car, which is in line with common sense. Directly aggregating PKO into the inference results of SGG models can improve unbiased performance of SGG models. The following is the display of experimental results of our solutions. We display the recall scores of each predicate category on mean recall at 50 and IMR at 20 for motifs reweight. We can see that the recall scores of the predicates underestimated by mean recall at K are more fairly evaluated on IMR at K. For example, the recall scores of the high correlated predicates, like wearing, of and watching, ascend significantly on IMR at 20 compared to mean recall at 50. While the predicate parked on has no obvious improvement on IMR at 20 as it is slightly influenced by the confidence suppression. Compared to mean recall, IMR provides a more fair score for these overestimated predicate categories. We also display the weights of different predicates in different metrics, recall, mean recall and WIMR. Recall mainly focuses on head predicates, although some head predicates have limited compositional diversity, while mean recall assigns equal weights to all predicates despite their difference in compositional diversity, and the samples of some predicates with limited compositional diversity like flying in are assigned excessively high weights. By considering both data distribution and compositional diversity, WIMR manages to assign high weights to predicates with rich semantics and low weights to predicates with simple semantics. In this paper, we focused on two overlooked issues which make the current evaluation benchmark vulnerable and unfair. We discussed the influence of these issues through statistical data analysis and provided two complementary metrics for unbiased SGG evaluation to address the two above-mentioned issues. We additionally investigated a statistical prior which reflects the intrinsic correlation between predicates and objects. Based on this, we devised a simple but strong baseline for unbiased SGG research. We hope that our work is able to contribute some insights to this area and help benchmark unbiased SGG methods in a more trustworthy way.